Miha Habic, and he is one of our former CUNY people, and it's great to have him joining the seminar again, one of the perks of the virtual seminars. And he's currently at Bard College at Simon's Rock. And today he will speak about normal ultrafilters with many sets of ordinals, or gotta catch them all. All right, Miha, go ahead.
Okay. Thank you, Vika, and thank you everyone for inviting me and coming to this talk. So I'm going to report on some results of joint work with Radek Honzik that we did quite a while ago at this point, but I thought it's still sort of a nice and interesting topic to introduce people to. All right, does this work? No. Okay. So let's see. The general setup of what I'm going to be talking about are elementary embeddings coming from large cardinals. Right? As we know, large cardinals tend to come with their associated elementary embeddings, so that the cardinal is the critical point of that embedding. And the embedding maps into some transitive inner model of the universe, all right? And based on how close that target model is to the full universe, we can calibrate the largeness of the critical point, right? So for example, if we want to describe measurable cardinals, then I can just have any model M as the target of my embedding. Anything is fine. And even if I work a tiny bit harder, I can get some amount of closure on the model M for free, right? I get closure on the kappa sequences for free. Then I can, of course, require more. I can require that M has any given set that you might like, or more generally, just computes an initial segment of the universe correctly. In that case, I get theta strong cardinals. I could require a more global amount of closure on the model closure under theta sequences for whatever theta you might like, and I get theta supercompact cardinals, and so on and so on and so on. The ultimate form of closeness of M to V, which would be that M is just equal to V, is inconsistent, as was famously shown by Kuhnen. All right, but I don't want to reach too far into you know, the large cardinal hierarchy. I want to stay pretty low at the level of measurables, right? So I'll be interested in ultra power embeddings by measures on the cardinal kappa. All right. So the main question that will guide us through this talk is, if U is a measure on kappa and M is the ultra power of the universe by that measure, how close is M to V? Right. So how close can I get a measure ultra power to V to V? All right. So from one side, I get, you know, a fair bit of closeness, right? So since M contains all ordinals and is closed under kappa sequences, we're going to get all subsets of kappa to be in M, right? Why? Well, because, you know, what is a subset of kappa but a length kappa binary sequence, right? Equivalently, we could restate this as saying that V kappa plus 1 is an element of M, right? So M computes the kappa plus first initial segment of the universe correctly. On the other hand, already at the next step, M will be incorrect, right? So V kappa plus 2 is not an element of M, right? So what M thinks V kappa plus 2 is wrong. And in fact, we have a concrete reason why M is wrong about this computation. This measure U that M arose from is never an element of the ultra power, right? If you've never thought about this, it's a very sort of fun exercise to go through, right? But basically the reason is that if U were an element of M, then M could attempt to compute the ultra power of itself by this measure, right? And because, you know, by the first point, M is reasonably close to V, the elementary embedding that M computes would be, you know, quite close to the elementary embedding that V computed, all right? And they would be close enough that if we looked at the ordinal k of kappa, if k is this embedding that M computed, then that would have to be the same as J of kappa. But on the other hand, J of kappa is inaccessible in M by elementarity, but M believes that K of kappa only has size that is accessible from kappa. So its size is 2 to the kappa as computed in M, right? So we get a contradiction here based on, at the same time, how close M is to V, but also how different they are, right? One of them sees J of kappa as inaccessible, and the other one sees it as quite accessible to kappa. All right, so what we're getting here is a concrete witness that M computes this initial segment of the universe incorrectly. All right, I have a little picture here. It's the same picture that everyone always draws in set theory talks. So we have V being embedded into this inner model M, and up to the level of kappa plus 1, these two models match up, but then just above that, the model M, the ultra power, becomes thinner, right? It's starting to miss sets. All right, so that's all well and good, right? So it seems like the model M matches up to the level kappa plus 1, and at kappa plus 2, we already get disagreement. So we seem to be done with the topic, right? Except that you can insert arbitrary amounts of complexity into this question, right? So the ultra power by a measure on kappa is missing this measure, which is an element of V kappa plus 2, right? And under GCH, this amounts to a subset of kappa plus, okay? So now we get into sort of two main questions, right? So first of all, for any ultra power, we found a set that is emitted from that ultra power, right? So can we make this a little bit more uniform? So is it the case that some sets of ordinals are emitted from every ultra power by a measure on kappa? Or possibly, could it be that any set of ordinals can be captured by some ultra power at kappa? So for each set of ordinals, I might have a different ultra power, but each one of them can be found in a model like this, all right? And then the same question we could ask in a more global way. So if GCH fails, is it possible that some ultra power captures the entire power set of kappa plus, right? So we're not only capturing, say, one subset of kappa plus at a time, each one with its own ultra power, but maybe there's one single ultra power that collects all of the subsets of kappa plus. And I don't even care that it's kappa plus necessarily. I could even ask for larger cardinals, lambda above kappa. All right, so if I go back to this picture, right? Okay, I made it seem like this thinning out of the ultra power. Can you see my cursor if I go like this? Yes, okay. So I made it seem like this thinning out happens already between kappa and kappa plus, but it's conceivable that if GCH fails quite strongly, then kappa plus could still be in the part of the ultra power that matches V exactly, and this thinning out at the level of V kappa plus 2 happens only much later than kappa plus. All right, so there's some quick observations that we can make about these two questions. So first of all, for question number 1, the local question where we're capturing one set of ordinals at a time, if we want a positive answer to this question, it's not hard to see that we need to require a good amount of largeness of kappa, right? For example, if kappa is the least measurable cardinal, and I take as my set of ordinals that I want to capture a set coding a measure on kappa, then no ultra power at kappa can capture that set, right? A measure on kappa cannot appear in any ultra power at kappa, because by elementarity, that would mean that there are measurables below kappa, but kappa was the least measurable, right? So unless we assume some largeness on kappa, then definitely there will be some sets of ordinals that cannot appear in any ultra power by a measure on kappa, all right? So that's that tells us that, we might have to stretch a bit in the large cardinal hierarchy. And then the other sort of nitpicky point is that often what can happen is that we have an embedding, some elementary embedding with critical point kappa that has a particularly rich target model, all right? And that target model might capture all sorts of sets of ordinals. And what we can often do in that situation is that we can factor out an ultra power by a measure on kappa that we design in a way that captures any given set of ordinals that we might like. All right, that measure on kappa is going to be, in general, relatively complicated, right? And we want to avoid this kind of, if you like, ad hoc construction of measures, right? So if we want to impose some kind of canonicity requirement, a good thing to try to do is to restrict these questions to just ultra powers by normal measures at kappa, right? So Rudin-Kiesler minimal measures. All right. So if we insert the word normal into these two questions, then question number 2 becomes something that was asked by Steele in 93. So he was wondering, is it consistent that a normal ultra power at kappa captures the entire power set of kappa plus? All right, so let's try to address these questions, and we'll go in order. We'll try to answer the local question first and then the global one. So just to introduce some terminology here, right? So we're going to define something called the local capturing property. So if kappa and lambda are cardinals, we're going to say that LCP, kappa lambda, holds if there is for each subset of lambda a normal measure of kappa whose ultra power contains that subset X. All right, so we're just capturing one subset of lambda at a time. So we already said that no measure ultra power can capture its own measure, right? But that's sort of a counterexample that's specific to each ultra power. If we want to have a kind of global counterexample, we can kind of step up a few ranks, right? And we can conclude that, okay, maybe each measure can be captured by some different ultra power, but if I try to capture the set of all measures on kappa, then no ultra power can capture that whole set, right? Because the model is transitive, it would also have to capture the measure that it itself arose from. Okay, so the set of all measures on kappa is, morally speaking, a subset of 2 to the 2 to the kappa. So what this argument shows us is that the local capturing property at 2 to the 2 to the kappa must fail, right? We gave a concrete example of a set that cannot be captured by a measure ultra power. All right, but this was quite a sloppy argument. We can bring the upper bound down a bit, and in fact we can prove that the local capturing property at 2 to the kappa plus fails already. So we can peel off one layer of cardinal arithmetic, if you like. All right, and this failure again is not that hard to see. A good way of thinking about it is, what would be an interesting subset of 2 to the kappa plus that we might try to capture by an ultra power? And a good idea might be a set of ordinals that somehow codes which ordinals up to and including 2 to the kappa plus are cardinals, right? So I can glue together a bunch of functions that witness that things that are not cardinals really are not cardinals, okay? And so if I glue all of these together, I get a single subset of 2 to the kappa plus. And if I try to capture that set in a normal ultra power, right, then I will get a normal ultra power M that computes all cardinals up to and including 2 to the kappa plus correctly. All right. But it's a fact that no normal ultra power on kappa can be this correct, right? For example, if you look at the two ordinals J of kappa and J of kappa plus, by elementarity, these are distinct cardinals in M, but in V, both of these ordinals have size 2 to the kappa, right? So if M was supposed to be correct about cardinals, then it should see that J of kappa and J of kappa plus are the same, but they are distinct as far as M is concerned. All right, so we got what seems to be an upper bound for where local capturing can hold. All right, and in fact, this upper bound turns out to be precise. If I peel off that one plus, I get a consistent principle, right? So we can show that LCP up to 2 to the kappa holds at any kappa that is sufficiently large. So 2 to the kappa supercompact is good enough, or even kappa plus 2 strong is good enough. And I'm not going to go through the proof of this, but this is essentially an old argument due to Solovay, that, you know, if you've ever seen an argument that tells you that any large cardinal like this, it has maximal Mitchell rank, then you've seen this argument of Solovay that gives you this amount of capturing, right? Or if you've seen a construction of a labor function, then you've more or less seen this argument of Solovay. All right, so this is quite interesting. We get direct implications from sufficiently large cardinals to this local capturing property. I have a little question here that I don't know how to answer, but I think is quite interesting. So in the proof that I didn't show you, you can deduce LCP kappa 2 to the kappa from 2 to the kappa supercompactness. All right, and in the argument, it really seems necessary that we have full 2 to the kappa supercompactness to get anything at all in terms of local capturing. So the question is, look, if I'm okay with having less local capturing, right? Maybe I want something, maybe I just want to locally have local capturing for subsets of kappa plus if 2 to the kappa is much larger than kappa plus. Would it then be sufficient to start with just a kappa plus supercompact, for example, right? So does theta supercompactness directly imply local capturing at kappa up to level theta, right, or not? So our argument seems to rely crucially on full 2 to the kappa supercompactness, and then we get the strongest possible conclusion from that, but we don't know if, you know, if we were willing to settle for a weaker conclusion, that we could start with a weaker hypothesis as well. All right. So we have an upper bound in terms of what LCP can do for us. We have a direct implication from quite large cardinals, but maybe we can do a bit better in terms of just consistency strength. All right. So in fact, we're able to give precise bounds in terms of consistency strength for this maximal amount of local capturing, right? So again, it's not very hard to see that if you have this maximal amount of local capturing, so up to 2 to the kappa, then kappa has to have maximal Mitchell rank, right? So if this is not something that you deal with, let me just remind you, the Mitchell rank of a cardinal is a measure of sort of the complexity of the set of normal measures on kappa, right? So for example, the Mitchell rank of kappa is at least 1 if kappa is measurable. It's at least 2 if there is a normal ultra power at kappa, so that in that ultra power, the Mitchell rank is at least 1, and then it goes on like this, right? So you're trying to see, can you build particularly rich normal ultra powers at kappa in which kappa has large Mitchell rank already. And if you sort of play around with this, you'll find that the maximal Mitchell rank that kappa could possibly have is 2 to the kappa plus, all right? Which is quite interesting because this matches up with this, with where local capturing can kind of get us. So it really plays nicely together. All right, so how do you see that local capturing gives you this high Mitchell rank? it really is just what you would want to do, right? So you're going to use the local capturing property to build a very long Mitchell increasing chain of normal measures, right? So what you're going to do is you're going to start with a normal measure, and you're going to apply local capturing to this measure so that you're going to place it in a normal ultrapower. But that normal ultrapower arose from a normal measure, and now you have the second normal measure that's Mitchell above the first one, all right? And now you can keep doing this. Now you can fit these two normal measures into a third normal ultrapower. So you get a third normal measure that's Mitchell above the first two. And you can keep going, and you can keep going, and keep going. And because you have local capturing for subsets of 2 to the kappa, you can keep going as long as your chain has length at most 2 to the kappa, right? So at the end, what you build is a chain of length 2 to the kappa plus. At that point, local capturing doesn't get you any further, but you cannot go any further, right? This is the longest chain that you could have, all right? So local capturing in this way gives you a very complex set of measures on kappa, all right? So this gives me, I guess, a lower consistency bound, right? So LCP implies something about the largeness of kappa in the universe, right? On the other hand, we can also get upper consistency bounds. I say below here, I think I meant above. So we can prove that if O of kappa is sufficiently large, at least kappa double plus, then this maximal amount of local capturing holds in an inner model, in this canonical inner model for a measurable of high Mitchell rank, all right? And so if you're, you know, depending on how familiar you are with these models, so this model satisfies GCH. So this amount of local capturing, so up to kappa plus, is the maximal amount, right? Kappa plus equals to the kappa. So we get as much local capturing as we could possibly want. So I'm not going to give, you know, the details of this proof, but it's, you know, if you've ever dealt with this model, it's relatively straightforward, right? What you use in the proof is that this U vector, the sequence of normal measures, is what's called a coherent sequence of normal measures, and that any subset of kappa plus in this model is constructed from some initial segment of this sequence of measures. All right, so if you want to capture this subset X, all you need to do is take the ultrapower by a measure on the sequence that appears after whatever initial segment you needed to construct X. All right, so once you hit the model with that measure, you get an ultrapower in which X will also be constructed. So yeah, it's not very complicated, but you know, as long as you know what this U vector is. In fact, in this model, you get a slightly stronger property than just local capturing. In fact, there's a single function f, so that whatever set X you want to capture, that function f is going to represent that subset of kappa plus. All right, so in this sense, you have a kind of labor function that guesses any subset of kappa plus that you might want if you pick the measure that you're taking the ultrapower by correctly. All right, so what we have at this point is, I guess, an exact consistency strength bound for the maximal amount of local capturing, right? So it's equiconsistent with a kappa of I guess, kappa of Mitchell rank kappa double plus. And we also have direct implications from quite large cardinals to the maximum amount of local capturing that we can have. All right, so let's move on to sort of the more global question, right? Let's try to now capture all of the subsets of kappa plus at once, okay? So we're going to define the capturing property, so throw away the local part. So again, kappa and lambda are cardinals, and we're going to say that the capturing property of kappa lambda holds if there's a single normal measure on kappa whose ultrapower computes the power set of lambda correctly, right? So this is like saying there's a uniform witness for local capturing at kappa lambda. Okay, so what we observed earlier was that the capturing property at kappa kappa just holds, right? So any normal ultra power at kappa computes the power set of kappa correctly. And the capturing property up to 2 to the kappa fails, right? Because there's always a subset of 2 to the kappa that's missing from a normal ultra power. What is it? Well, it's the measure that the ultra power comes from. Okay, so Steele's question, if you remember, asked about the consistency of this capturing property at kappa kappa plus. Right, so this question was answered by Cummings again in 1993. So this is an example of a weird situation that sometimes happens where the answer to the question appeared in print before the question appeared in print. So it's a weird time paradox that happened in 1993 that, I don't know, maybe all of the entire universe will collapse now that I've brought attention to it, but anyway. So what did Cummings prove? He proved that this capturing property at kappa kappa plus is consistent relative to a kappa plus 2 strong cardinal kappa. All right, so so what he managed to do was to start from a relatively large cardinal and force to a model of this capturing property. Okay, and moreover, he proved that this large cardinal hypothesis is optimal. So if this capturing property holds, then kappa must be kappa plus 2 strong in an inner model. All right. Let me just maybe comment on the large cardinal hypothesis here, right? So based on what we said before, this capturing property at kappa kappa plus implies that GCH must fail at kappa, right? Because kappa plus must be smaller than 2 to the kappa for this capturing property to even make sense, all right? And so having a measurable where GCH fails, results of Gittig then show that we need more than just a measurable to make that happen, all right? And the kappa plus 2 strong cardinal is just a tiny step beyond what Gittig required to get the failure of GCH at kappa, at a measurable kappa, all right? So it seems, very appropriate that this is what was needed for the capturing property, right? You needed some amount of strength to make GCH fail, and then you needed just a tiny bit more to additionally get this capturing property to hold. All right. So now I want to move into, I've been telling you mostly what was already known and some, playing around with ultrapowers, right? Let's try to see what sort of the main result that I want to show you is. So the capturing property at 2 to the kappa fails, as we saw. And local capturing at that level is consistent, but it just directly implies that kappa is large in V, right? Remember, it told us that kappa has large Mitchell rank in V, all right? Okay, so let's back away from 2 to the kappa a little bit and focus on kappa plus. So if GCH fails at kappa, okay, then, by Cummings, we know that CP kappa kappa plus implies that kappa is large in an inner model, but it doesn't really say anything about the size of kappa in V, at least not apparently, all right? So the question is, can we get direct implications about the size of kappa in V from weaker forms of capturing, or maybe even local capturing? So let's say, if I have capturing at kappa kappa plus, or maybe even just local capturing at kappa kappa plus, does that imply anything about the size of kappa in V, like having the maximal amount of local capturing did? Okay. So what Radek and I managed to show is that there are no implications like that. Okay, so we showed that it's consistent relative to a kappa plus 2 strong cardinal, that this capturing property up to kappa plus holds, at the least measurable cardinal kappa. Okay, so we can make kappa just be the smallest measurable cardinal in V, and capturing still holds there. All right, so I wanted to tell you something about how you go about proving a result like this, because I think the methods are very interesting and should be fruitful for further exploration. Okay, so how do you produce a normal measure / an ultra power that captures the entire power set of kappa plus? All right, so maybe it's unclear what you would want to do, but okay, let's try to do it very naively. All right, so step one, I don't know how to do it with a normal measure at kappa, but I can just start with a sufficiently fat embedding from V to M that captures the entire power set of kappa plus, right? But might not be a measure ultra power by a normal measure on kappa, right? Okay, if I assume that kappa is large enough, then I get an embedding like this, okay? Then I know that if I want to have this capturing property, if I want to capture the entire power set of kappa plus, I need to make GCH fail at kappa. All right, so I do my best to force to an extension where GCH fails at kappa, so maybe 2 to the kappa is kappa double plus, and then lift this embedding that I started with to some J star, some lifted embedding. All right, and then I sort of run out of ideas, and I hope for the best, and I kind of sit around. And what saves us is the following fact that is implicit in what Cummings did, but wasn't really spelled out in any explicit form. All right, so what this fact says, very roughly, is that if you have a nice elementary embedding J with critical point kappa, that you can lift to a forcing extension in which 2 to the kappa is large enough, then this lift, J star, is just going to turn out to be automatically an ultra power by a normal measure on kappa. All right? So I'm sweeping a lot of stuff under the rug here. All right? I didn't tell you what a nice elementary embedding is. I didn't tell you what 2 to the kappa being large enough means. All right, but maybe it's good enough for now to just say, look, if I can have this fact work for me, then this strategy that I outlined above here should just work, right? So if I start with a sufficiently fat, nice embedding J, okay, and then force to make GCH fail, then this lift J star is just going to turn out to be a normal ultra power at kappa. And so, it should just witness the capturing property in the extension. All right. So this is the strategy that I'm going to try to build on. Okay, this is the strategy that Cummings used to produce a model of CP kappa kappa plus. All right. Now we want to take this strategy, and we have an additional goal. We also want to make kappa be the least measurable. So we need to build that into our argument somehow. All right. So what we need to do is, okay, we're going to start with a fat embedding again. Okay. But the forcing that we do now has to make GCH fail, but it also needs to kill all of the measurables below kappa. Okay. So you might, okay, if I give you this as a homework assignment, then you might sit down and say, all right, I don't know, I'll try some stuff. I know, Cummings told me how to make the capturing property work, and I know some different ways of how to make kappa be the least measurable. So maybe I'll do the capturing property first, and then I'll do some more forcing to make kappa be the least measurable. And I don't know, maybe something magical will save me again, right? But there's a tension here, right? So if you want to take this, if you want to force the capturing property first, then okay, you have an embedding that a normal ultra power that captures the entire power set of kappa plus. Okay, and then you want to lift this embedding probably to an extension where kappa is now the least measurable. So you're going to kill all the measurables below kappa. Now, you probably can imagine that if you want to live this embedding, then you probably also need to, at some point in your argument, kill the measurability of kappa and then resurrect the measurability of kappa, right? Because on the J side, your forcing needs to stretch all the way past kappa. Okay. Okay, maybe you even know how to do this. But what I found is that, the majority of ways that at least I knew how to kill and resurrect the measurability of kappa, all of these were visible at the level of the power set of kappa plus. Okay. Why is that a problem? That's a problem because if at the end of the day you want to end up with, a target model that sees the entire power set of kappa plus, and you've killed and resurrected the measurability of kappa that in a way that is visible to the power set of kappa plus, then the J side of your final embedding is going to see that kappa has been resurrected. And then by reflection, on the V side, you're going to have a measurable below kappa. And now you failed in your entire pursuit and you give up and you go do something else. Okay? So the point is that you shouldn't give up, right? But what you should do is try to find a way of killing the measurability of kappa in a way that's not visible to the power set of kappa plus. All right? And then you might have a hope of killing and resurrecting the measurability of kappa in a way that won't be seen by the J side of the model of the embedding that you'll end up with. Okay. So what you do is you find a paper by Arthur and Schellach where they have this method of adding kappa double plus many subsets to kappa in a very sneaky way, in a way so that these kappa double plus many subsets won't be able to be measured at the same time by any countably complete ultrafilter on kappa. All right. All right. So let me show you what this forcing looks like, because it's quite nice. All right, so this slide has a lot of setup and verbiage. So I'm going to skip this slide for now, and I'm going to show you a picture. Okay, and maybe we'll come back to this slide. So what does this forcing look like? Well, you take two cardinals, gamma and delta, okay, and you're going to sort of set yourself up in a situation where you're pretending basically that you're adding delta many Cohen subsets to gamma, basically. So you have this matrix that you're filling in with zeros and ones, and a condition might fill in some of these columns and leave others blank, and so on and so on. All right. In addition to this working part, you're also going to have a side condition, and the side condition is going to have certain collections of countably many columns in this matrix. Okay, so maybe one of these countable collections is pictured here with the green columns. All right, so the slide was too small for me to be able to draw countably many columns, but you get the idea. All right, so the side condition has several of these different collections of green columns. All right, and the side condition comes into play when I want to strengthen my condition. So how do I strengthen a condition like this? Okay, I strengthen it by strengthening the working part, so the Cohen part. All right, but I need to pay attention to these green columns. So I put an additional restriction, and I say that within each collection of these green columns, okay, when I strengthen the working part, I am not allowed to put a whole row of zeros or a whole row of ones. So each row, when restricted to a set of green columns, needs to sort of alternate. Okay. If you think about what this means, right, the side conditions are basically telling me, look, the generic sets that you're going to add on these green columns, they are never again allowed to have a common element in their intersection, right? That just means that there's no row of just ones on these green columns, okay? After I've, started considering that side condition. And also their complements never again get a new element. That means just that, whoops, that just means that there isn't a whole row of zeros when restricted to these green columns, all right? So basically what we're doing is we're going to add, hopefully delta many subsets to gamma, all right? And if I pick my, my side conditions correctly, then I'm going to have a bunch of countable collections of these new sets that I've added, whose intersection will be bounded in gamma. And the intersection of their complements is also going to be bounded in gamma, okay? And if you sort of, gaze ahead, you can kind of see the outlines of maybe trying to prove that, this collection of green columns cannot be in a countably complete ultrafilter at the same time because their intersection is small, it's bounded in gamma. And their complements also cannot be in an ultrafilter because the intersection of the complements is also small. All right, let me give you some of the verbiage about the forcing now. Okay, so we're going to fix an inaccessible gamma and a bigger delta that's regular. Okay, so these are going to be these are going to specify my working part of my condition. So the working part of a condition is just going to be a uniform Cohen condition in this Cohen forcing at gamma delta. Okay, now the additional sort of stuff that I'm carrying around with myself is a non-reflecting stationary set S. So it's a subset of delta, but it concentrates on cofinality omega points. And I fix an S ladder system X vector. So what does that mean? X vector is a sequence of sets indexed by S, and each X alpha is an omega sequence that's cofinal in alpha, right? So I fix a bunch of witnesses that things in S have cofinality omega. Okay, so these sets X alpha, these ladders, as they're called, are going to be the stuff that I put into my side conditions, right? So a side condition Z here is a subset of the ladder system, and okay, there's an additional requirement that requires that if I put a ladder into the side condition, then the working part needs to have said something about every column that's specified in that ladder. All right. And this is just to make sure that I don't start putting in ladders into my side condition without the working part saying anything about those coordinates. Okay. So like I already said, the side condition contains promises that the intersection of those countably many columns or their complements will never get a new element if I strengthen from a condition that has that side condition. All right, now, fine, this is a forcing, it's great, but you should be a little bit worried. Why should you be worried? Well, because it's not clear at this point that this forcing even does what you want it to do, right? The basic thing that you would want it to do before anything else is it should fill in this matrix. It should add delta many subsets to gamma, right? And the way I've set it up, maybe it's not clear that that can actually happen, right? Because conceivably, it could be that the ladders, right, the collections of green columns like this in a side condition could interfere in a way so that if you try to make one collection of, if you try to satisfy the requirements of one collection of green columns, right, maybe that forces you to violate the requirement on another collection of green columns, right? Maybe they sort of intersect in complicated ways that just make it so that some conditions are atoms, they can no longer be strengthened in a useful way, and that's not what we want. Okay. In fact, that's not what happens, right? What you can do is some amount of combinatorics where you use the fact that you've set yourself up in a particularly nice way. You use the fact that your ladder system is based on this non-reflecting stationary set. And what that allows you to do is basically pretend that a lot of these ladders are just pairwise disjoint, okay? And that's sort of, you know, the content of this lemma, right? The lemma says that if I have a bunch of ladder systems that are supported on, if I have a ladder system that is supported on a non-stationary set, all of whose initial segments are also non-stationary, then all of these ladders can be disjointified, by which I mean you can pick a tail from each ladder so that all of those tails will be pairwise disjoint, okay? How is that helpful? Well, first of all, it helps you prove that you don't get into those problems that I was describing. You really do force that there's delta many new subsets of gamma, and in fact, you force that 2 to the gamma is equal to delta, right? Because at that point, you can just, you know, replace whatever ladders you have in the side condition with the pairwise disjoint tails. And at that point, your conditions, you know, in your conditions, you can basically just ignore the side condition completely, right? You can just pretend that you're working with co-enforcing, just plain co-enforcing, because the ladders in the side condition don't interact at all anymore. They're just pairwise disjoint.
Miha,
Right?
Miha, could I just ask quick? The set S in the definition of the forcing, was it meant to be stationary and non-reflecting, or?
It is stationary and non-reflecting.
Okay.
Right? So the way you use this lemma to prove this unsurprising fact is you show that, so you want to show that any condition can be strengthened to fill in any part of the matrix that you want, all right? But the condition only mentions a bounded collection of ladders, right? So you apply the lemma to an initial segment of the ladder system, and that is supported on a non-stationary set, right? The full set all the way up to delta is stationary, but every initial segment is non-stationary.
Okay, and in the application, in the application then you force to add non-reflecting stationary sets? Or
yes, we're going to force to add those, yes.
Okay.
You first force to add a non-reflecting stationary set of ordinals of some fixed cofinality. It doesn't have to be cofinality omega. It can be some fixed regular cardinal, but it has to be of some fixed cofinality. And then you do the fancy type of forcing that Miha has been describing. By the way, the presentation that Miha is giving is very different from, or at least somewhat different from, the presentation that Shelach and I give in the 2 papers that we've written on the subject. So if by some weird chance you decide that you want to try to look at the original source, I think you're better off looking at what Miha is doing. It's going to be clearer.
So I would say with the conclusions that Arthur and Sherlock, you know, pull from their more complicated setup are also stronger. So we're going to see that this forcing is preventing there from being even countably complete ultrafilters on kappa. What they get out of their more complicated setup is they can control the degree of completeness of ultrafilters on kappa, and that goes into controlling the degree of strong compactness that you can have on kappa, and so on, right? So they were going for a stronger result than Radek and I were, so you know they needed a different setup.
And also what we get is an alternate way of proving a theorem originally due to Wooden, which is that it's consistent that the least measurable can be kappa plus supercompact. Wooden originally proved this using Radon forcing. His proof has never been published. It is in the notes on radiant forcing that Cummings and Wooden have written, which allegedly is supposed to become a book. I say allegedly because it hasn't happened yet, and these notes are, I don't even know, 30 years old, however old they are. We have an alternate, Shelach and I have an alternate way of doing this with the type of forcing that is being described, or at least a more complicated version. You are able to take a kappa plus supercompactness embedding, let us say, and then do this kind of forcing and lift the embedding into an inner model, which still the lifted embedding still witnesses kappa plus supercompactness, but the key fact is that in the target model M, kappa is not measurable, and then you just kill the measurables below and you're going to get what you want. But anyway, this is the more complicated thing that Shelach and I do. Okay, sorry, Miha, go.
Yeah, it's very insightful to, I really think this technique has a lot of fruit left to yield. So, it's very exciting. All right, so the unsurprising fact was that we actually do what we wanted to do. We add delta many subsets to gamma. A slightly more surprising fact is that, this allusion to co-enforcing isn't just accidental, right? So imagine now that, you have this non-reflecting stationary set that you used to build the forcing, and now you shoot a club that kills the stationarity of this set S, all right? And what you can show is that in the extension where you've killed the stationarity, this Apter-Shelach forcing is just equivalent to plain old vanilla co-enforcing at gamma delta, okay? And this is basically just, the same argument that we saw for why the matrix gets filled in, but now the entire matrix, the entire ladder system is supported on a non-stationary set, so you can just run the same argument basically for the entire ladder system at once.
Miha, is this forcing like gamma strategically closed or something like that?
Yes, it's strategically closed.
So the way I set it up, it's even better than strategically closed. And the reason is because I require that the working part is uniform in the sense that all the non-empty columns have the same height. If you relax that requirement, you get strategic closure, but not full closure.
Right. And by the way, just let me comment that calling it the Apter-Shelach forcing, that's putting it in alphabetical order. If you want to really call it, it should be Shelach in big, bold letters and Apter in tiny, tiny little letters. The major ideas are due to Saharon.
So I should also say, I use the letter A here for this forcing. This is not because I want to diminish Shelach's contribution at all. It's because I see this forcing based on very much on co-enforcing that I write as add. If someone ever designs a forcing based on something else that works in a similar way, I would, maybe call it something else. All right. So what we have now is basically an idea that this Apter-Shelach forcing is going to make, if I do it properly, make GCH fail. It can add many subsets to gamma or to kappa, if you like. And then if I do this club shooting forcing, then that seems to give me a good way of, provided that I can show that this A forcing kills the measurability, then shooting this club might give me a way of resurrecting the measurability, because after adding this club, the operative forcing is now just co-enforcing, and that seems not very destructive at all. But we'll see how it goes. We should first just convince ourselves that the Apter-Shelach forcing really does kill the measurability of kappa. All right. And for that, I need an additional ingredient to the setup, okay? So not just any ladder system is going to be good enough. I'm going to need a slightly souped up ladder system that, you know, if you want, you can think of it as a diamond sequence, but what I really need is something called a club delta sequence, all right? So delta is regular and S is a stationary subset of delta, then this club delta of S sequence is a ladder system like what we had, so a sequence of these X alphas, that has a particular guessing property. So for any unbounded A subset delta, there is some alpha in S. So there is some ladder in this ladder system that gets inside the set I'm trying to guess, all right? So this is kind of like diamond, except that I'm not requiring exact matching, right? I'm only requiring that, you know, my guess gets inside the set, all right? So I'm going to, I'm not really sure if this is the case. So if delta is omega 1, then this club principle is exactly the fragment of diamond that is left over if you throw away CH, right? So diamond at omega 1 is equivalent to a club at omega 1 principle like this plus CH. I'm going to speculate, although I'm not sure, that the same should be true at, well, I don't know, I take that back. Maybe it's not true. I was going to say that the same might be true at uncountable delta, although diamond at uncountable diamond at delta larger than omega 1 tends to just be a GCH assumption anyway. So I'm not really sure what I wanted to say there. But think of club as a fragment of diamond, if you like. All right. And so what is the point? The point is that if I start with a club sequence like this, if X vector is a club sequence, then the Apter-Scheller forcing is going to make, so if I do it at gamma, comma, delta, comma, this club sequence, then it's going to force that gamma is not measurable. All right. And maybe I'm going to skip the proof right now, but just as a kind of basic outline, right? What is going to happen? You're going to have, so you might as well pretend that you have a condition that forces that all of the generic columns, so fix a name for a measure on kappa thing, or a measure on gamma. And then you have a condition, say, that forces that all of the columns in the generic matrix will have measure 1 after you're done, all right? So then what you can do is you can use this club sequence to find a ladder so that all of the columns on that ladder are being forced to have measure 1. And then you can find a stronger condition by adding that ladder into your condition. And now this stronger condition is forcing that those columns have bounded intersection. But before, you forced that all of those columns had measure 1, and therefore if you know the measure was counted to be complete, then their intersection would have to be unbounded. So that's the way you get into a contradiction. If you used the more complicated forcing, well, one version of the more complicated forcing that Arthur mentioned, where you use different cofinalities than just cofinality omega, then, you know, in this argument, you can make the ultrafilter U not be, I don't know, epsilon complete for some degree epsilon, but complete, you know, below epsilon, if you like. Anyway, so what we have now is, provided we set ourselves up correctly, is we have this forcing A that can add loads of subsets to kappa, can kill the measurability of kappa, and then, you know, hopefully we can resurrect the measurability of kappa if we then shoot that club, you know, and transform this forcing into plane cone forcing. All right. So this gives us an outline of what we want to do. So recall, what are we doing? we're starting with a kappa plus 2 strong kappa, and we're trying to force to an extension where kappa is the least measurable, but still the capturing property at kappa kappa plus holds. All right. So we're going to start with a fat embedding coming from this kappa plus 2 strong kappa. This fat embedding captures, you know, all the subsets of kappa plus and much more. And we define this forcing iteration, right? So at every inaccessible gamma less than kappa, we're going to force with this S gamma double plus, which is going to add a non-reflecting stationary set. And then after this, we force with the Apter-Scheller forcing to add gamma double plus many new subsets to gamma using this club gamma double plus of S dot sequence, right? S dot was the non-reflecting stationary set that we added. You might ask, where does this club sequence come from? And you can show that this non-reflecting stationary set forcing just adds a club sequence like this. It's not very hard. If you've ever shown that, you know, adding a Cohen subset to omega 1 adds a diamond sequence, this is very similar. Right? It goes in very much the same outline. All right, so this iteration up to kappa is going to kill all the measurables below kappa by design. Okay, so now we need to do something at kappa. Okay, so we want to lift J, so we need to do more forcing. And the more forcing that we do is, okay, the iteration up to kappa, then we add this non-reflecting stationary set at kappa double plus, and then we do the Apter-Scheller forcing to kill the measurability of kappa, and as a product, we then shoot this club to kill the stationarity of S dot. Okay. So using what we've seen already, this whole iteration is equivalent to just the iteration up to kappa, and then these two stages of just plain Cohen forcing. So first, we're going to add a Cohen subset to kappa double plus. Okay, this comes from first adding the non-reflecting stationary set and then killing it, and then adding kappa double plus many subsets to kappa, which is what comes from this Apter-Scheller factor.
Right, it's a club disjoint from the non-reflecting stationary set.
Yes. Okay, so with this alternative presentation of the iteration, it's not that hard to believe that this full forcing P is going to, okay, it still kills all the measurables below kappa, but then you can also lift J through this forcing provided that you prepared your original model to start with, okay? And then, you know, our strategy is basically complete, right? Then using the key fact from a long time ago, okay, we started with a fat embedding. It was, you know, a nice embedding, if you believe me that I'm telling you the truth. And now we've pushed up to the kappa. So once I lift the forcing, lift the embedding through this forcing P, the lifted embedding is just going to be the normal ultra power by a normal measure. And it witnesses the capturing property kappa kappa plus because the original embedding did, and the chain condition of this forcing is not too bad. All right. So this gives us what we wanted, right? Now we have a model where kappa is the least measurable, and yet there's an ultra power that captures all the subsets of kappa plus. Okay. So just in the final few minutes, I want to give you some variations on the theme of this result that we can get without too much extra work. Okay. So this iteration actually already appeared in one of the papers that Arthur and Scheller wrote, where they introduced this forcing. And like he said, they used it to produce a model where the least measurable is kappa plus supercompact. Okay, and if you sort of look at it, you can combine the two results. Okay, if you start with, you know, enough hypotheses, you can combine the two results to get a sort of conglomerated theorem. So if you start with a kappa plus supercompact kappa, then you can force to an extension where kappa is the least measurable is kappa plus supercompact, and also the capturing property holds at kappa comma kappa plus. All right, so you can sort of add on properties to this model that we have to get sort of more exciting constellations of properties. Another thing is you're not sort of constricted with just staying at capturing at kappa plus. You can play around with the values of 2 to the kappa to capture other power sets as well, right? Again, you should start with a stronger hypothesis. But you know, if you have kappa and a bigger cardinal lambda with an appropriate cofinality restriction, then you can force to a model of the capturing property kappa less than lambda if you start with an H lambda strong cardinal kappa. And in that model, 2 to the kappa will be equal to lambda, right? So CP kappa comma less than lambda, you can imagine what that is. You get one normal ultra power that captures all the subsets of so every power set of theta less than lambda, right, at once. Okay, and given that,
Miha?
given this value of the continuum, this is the best amount of capturing that you can have in that situation. Yes.
Does this forcing preserve cardinals less than lambda?
Does this forcing preserve cardinal?
Probably. Oh, I'm just asking because that would make the theorem more interesting.
I think it does.
I think so. I think so. So the preparation that you do for this result is slightly different than what Cummings did for his original result. And I have to say, I don't remember offhand if that preparation does damage to the cardinal structure between kappa and lambda. As far as the forcing that you do from the prepared model to the model where, you know, this theorem holds, I think you preserve the cardinal structure between kappa and lambda. I don't think any forcing that you do collapses anything.
If you're talking about the forcing that Saharon and I do, if you do what might be characterized, at least Cummings and I characterize it in one of our papers as the simple version, then you're going to preserve all cardinals. But if you take a look at a more complicated version of the forcing, which is also it's presented in the second of the two papers that Shelach and I wrote, it's going to collapse one cardinal along the way with the iteration. So in other words, when you get up to kappa, if you're making 2 to the kappa equals lambda with the more complicated version of the forcing, then you're going to collapse kappa plus. But if you use, again, the, so to speak, simpler version of the forcing, you don't collapse anything.
All right, so if you start with a sufficiently strong cardinal, you can get capturing up to, you know, any value of the continuum that you like. And in fact, the consistency strength here is optimal, right? So we can also go in the other direction. If you have this amount of capturing, so kappa less than lambda, then kappa will be H lambda strong in a model. I think that's right. Okay. There's an inner model with an H lambda. Okay, either kappa is H lambda strong in an inner model, or there's an inner model with a fully strong cardinal. Let me just say that. Okay. Anyway, morally kappa is H lambda strong in an inner model. All right. We can also sort of, all of the examples here had capturing all the way up for as long as you could go, right? All the way up to the continuum. But we can also get the failure of capturing to happen strictly below 2 to the kappa, all right? So one example of this is this sort of weird constellation of properties. So if you start with GCH and kappa being H kappa plus 3 strong, then there's a forcing extension in which kappa is the least measurable. 2 to the kappa is kappa plus 3. And capturing up to kappa plus holds, but capturing at kappa double plus and even local capturing at that level fails. Okay, so we get sort of a one-step gap, if you like, between the continuum and the bound for the capturing property. It's sort of interesting to think about the large cardinal hypothesis here. If you ignore the first line of this theorem, you would expect the constellation of results here to be possible just on consistency strength grounds. So we conjecture that it's possible to force 2 to the kappa equals kappa plus 3 and the capturing property at kappa plus, starting from an h kappa plus 2 strong cardinal and starting from a cardinal that's h kappa plus 2 strong and kappa plus 3 tall. So you need the tallness to get the continuum to be kappa plus 3, and you need the strongness to get this capturing property. And this constellation, as far as we can tell, is weaker than an h kappa plus 3 strong cardinal kappa, which is what would be required for capturing at kappa plus plus. All right. So if we knew how to force, 2 to the kappa is kappa plus 3 and CP kappa kappa plus from what seems to be the optimal hypothesis, then we wouldn't have to do extra work to show that CP kappa kappa double plus fails, because we would know that it fails based on consistency strength grounds. But for our argument, we seem to need crucially this stronger assumption, like the full h kappa plus 3 strongness. And then we needed to do extra work to see that we got capturing at kappa double plus to fail. All right. So I think this is, calibrating the exact large cardinal you want to start with here is sort of an interesting question still. All right. For my last slide, I want to give a slightly different perspective on how you might think about the capturing property, which was kind of surprising to me, honestly. So instead of measuring largeness directly, right? So remember, the main question was, does capturing at kappa plus imply the largeness of kappa in V, right? And it didn't, using the conventional measure. But another way of thinking about it might be, look, if you have capturing kappa kappa plus, fine, there's one normal measure on kappa that's particularly fat, that captures a lot of stuff, okay? But you might expect that regardless of that, there might be other much thinner measures that don't capture really anything at all, right? You could think of this in analogy with for example, no matter what measurable cardinal kappa you start with, there's always a measure on it so that in the target model M, kappa is not measurable, right? There might be other measures in which kappa is very much measurable and have other properties as well, but there's always at least, there's always one where kappa is not measurable in the target, okay? So honestly, I expected this to be the case here as well, right? So that even if the capturing property holds, you could just prove that there is always a measure that doesn't capture, much. And this turns out to be false, okay? We can prove that it's consistent, again, relative to a kappa plus 2 strong cardinal, so if you start with a kappa plus 2 strong cardinal, you can find another model where kappa carries a unique normal measure, but that unique normal measure still witnesses the capturing property at kappa plus. So there's one single normal measure in kappa, and yet that measure is quite fat. All right. So if you're at all familiar with the work that went into the number of normal measures problem, I don't know, more than 10 years ago at this point, I think. The model for this is just the Friedman-Magador model, all right? So their model where they have a measurable kappa with a unique normal measure and a failure of GCH, you can show that in that model, that unique normal measure witnesses the capturing property, all right? What is interesting, though, is that it's not clear at all how you would combine these methods controlling the number of normal measures in kappa with the methods to make kappa be the least measurable cardinal. Sort of the techniques that Friedman and Magato used are very different from what we've seen in this talk, and finding some combination of that and getting kappa to be the least measurable in addition to all of these other properties, I think is a very interesting question that I've sort of been dabbling in, and you know, I'm still not there, but I hope to at some point get somewhere. Anyway, I think I'll stop now, but thanks everyone for your attention, and if there are questions, I'm happy to answer anything. Thank you.
Great, Miha. Thanks very much for this super interesting talk. Let's thank Miha in any way we can on this format with its limitations. Questions for Miha?
Actually, I have a question. Can you go to slide 10, please, page 10?
Mm-hmm.
Okay. So let me just ask. So you're saying that results of GITIC show that non-trivial consistency strength is required. Are you saying here, because it seems to be saying that 2 to the kappa, that what's required is because kappa is measurable to get 2 to the kappa is greater than kappa plus. Is that what you're referring to by results of GITIC?
Yes, that's what I meant.
Okay, so actually I want to give a slight correction there. Mm-hmm. So the person who originally showed that GCH failing at a measurable is stronger than a measurable cardinal is not GITIC, it's CUNY. So CUNY showed, and this, I believe this may be in his 1970 Annals of Math Logic paper on iterated ultrapowers. So what CUNY showed is that if GCH fails at a measurable, then using iterated ultrapowers, you can get for every ordinal theta, you can produce an inner model with theta many measurable cardinals. So it's actually the fact that GCH failing at a measurable is stronger than a measurable is due to CUNY.
I see. All right. All right. But it's still the case though that the exact consistency strength of the failure of GCH at kappa is due to GITIC.
Absolutely.
If I'm not mistaken.
Yes, I mean it builds on earlier work of Wooden, but yes, GITIC pinned down exactly the consistency strength. But just the fact that it's stronger than a measurable is due to CUNY.
All right. Yeah. Okay. Thanks.
Any other questions for Miha?
I guess I have a question. On page 7, I think it is. Right, so you have that question there. I guess I don't remember exactly or whatever how that argument would go in the proposition, but is there a reason why you have like the theta matching with the LCP and the theta super compact? Or
well, the reason why I have it matching is because, I don't know, that seems to make sense to me, right? So if I have a theta supercompact kappa, right, then I have some embedding into some model where all of the subsets of theta are there, right? And what I'm asking for is that good enough for me to just be able, I don't know, to factor out a bunch of normal ultrapowers that capture each of those subsets of theta, right? I mean, it's interesting, right? So the proof of this proposition, this argument of Solovay, it's not a direct proof, right? It's a proof by contradiction, actually, right? So you assume that some subset of 2 to the kappa isn't captured, and then you do some stuff and you draw some diagrams and so on and so on. And then you see that that leads you to a contradiction, right? But it's not as simple as saying, well, I have this, you know, this arbitrary embedding that captures everything that I want, and then I just do some simple factoring to get these normal ultrapowers that capture one set or the other, right? And in that argument by contradiction, you seem to really, you know, crucially use the full 2 to the kappa supercompactness, right? And if you don't have that, if you just have theta supercompactness for some theta less than 2 to the kappa, I mean, you just cannot run that particular argument, right? And I don't know of a different way of just deducing LCP from you know, theta supercompactness.
Thanks.
Anyone else? All right, then let's thank Miha again for his talk with my favorite Zoom icon here. Okay, so next week we have Mirna Jamonia. Then we're going to take a break for September 11th. And after that, we will have Arthur speaking.